So yesterday we talked about our vectors and we talked about some of the basic ideas behind vectors. And we said that the standard representation of a vector is a vector that's at the origin, but not all vectors begin at the origin. They can start and end at any point in a plane. The place that the vector begins and ends does not really affect the vector in any way. So if we have one vector that has the same length, that has the same direction, then we would say that those two vectors are equivalent vectors. So u and v in this case are equivalent vectors because they're both going up 4 units and over 3 units, right? They don't start in the same place, but they go the same distance, they have the same length, and they have the same direction. So there's this rule called the head minus tail rule, which we're not really going to use, but you should at least have once in your life heard of it and been exposed to it very, very briefly. So if your arrow for your vector has an initial point of x1, y1, and a terminal point of x2, y2, it can be represented as x2 minus x1, comma y2 minus y1. That's called the head minus tails rule. And so it represents that standard representation of the vector x2 minus x1, comma y2 minus y1. We don't really need to do anything with that. What we do want to be able to do is figure out the magnitude and direction of vectors and figure out what they are in their component forms if we give a magnitude and a direction. So we want to be able to go from the vector -1 root 3 to being able to tell me what its magnitude and direction is, and also going from a magnitude and a direction to this component form in the angled brackets. So this is our first goal for the day. Should be pretty straightforward, hopefully. How are we going to find the magnitude of -1 root 3?
Pythagorean theorem.
Yep, all it should be is the square root of -1 squared plus root 3 squared. This ought to be the square root of 1 plus 3, or it ought to be 2. And we would say that this is the absolute value of v. That's the magnitude of this vector. And everybody good with that?
Yeah.
How are we going to find the direction of this vector?
Inverse tangent. Oh, sorry.
Yep. Inverse tangent of the y component over the x component. So this is the inverse tangent of -√3. And which quadrant does this need to be an angle in?
Two.
Second quadrant, right? This is just like with our polar stuff. This is in the second quadrant. And so what angle in the second quadrant gives you -√3 as its tangent?
2
2
pi.
pi.
2 pi over 3. So this is a vector with a magnitude of 2 and a direction of 2 pi over 3. Good or no?
Is there a notation for the direction? Like you have absolute value of v as the magnitude or something like.
I mean, just theta equals would be
theta.
Yeah, theta would be all it would be. All right. How will we find the component form? So the angled bracket thing right there, -1 root 3, let's say, for a vector that has a magnitude of 4 and a direction angle of 30 degrees. That's going to look something like this, right? The length of 4 here. So how am I going to find the x and the y components of that vector?
For x, you can use the cosine of the angle, and then for y, you can use the sine.
So x equals what times the cosine of that? Yeah, 4 times our cosine of 30, and our y should equal 4 times our sine of 30. And what's the cosine of 30?
√3/2.
So we've got 4√3/2, and over here, well, which is 2√3. And here we've got 4 times a half, or just 2. So our component form for this vector should be first quadrant, right? And the x component is 2√3, and the y component is 2. Good or no?
Great.
All right, cool. So here are some more rules, things that we can do with our vectors that we just sort of need to know these basic operations for. So take a look at those, and then we'll talk about them in a second. So first off, we talk about k. K is some real number that we're going to multiply by some of these vectors. We call that a scalar. So you can multiply vectors by a scalar, by some constant, basically. And if you try to multiply an entire vector by that scalar k, then you just distribute it to both of them. If I want to find the sum of two different vectors, I just add together their x components and add together their y components and write a new vector. We might need to find the opposite of vector. Opposite of vector is just defined as the -1 times that vector. And there's officially no vector subtraction. We just define vector subtraction as adding the opposite vector to our vector. Everybody good with all of those?
We have 1 more second to write it down.
Sure. Everybody good there now?
Yes.
Okay. All right. So we're going to do a couple of quick operations with vectors just to make sure we sort of get this stuff a little bit. 2u plus 3v. So 2u means we're taking the vector u and multiplying it by a scalar of 2. So what is 2u equal just by itself? 2u should be what?
-2,6.
-2,6. And what should 3v be? Ought to be 1221, right? And if I want to add those two together, 2u plus 3v ought to just equal the sum of the x components and then the sum of the y components. So -2 and 12 ought to give you 10, and 6 and 21 ought to give you 27. Easy enough?
Yes.
Yeah.
No issues there? Okay. If we want to do u minus v, that ought to be the same as u plus the opposite of v, right? Based on how that's defined for vectors. So this ought to be the vector -1, 3 plus the opposite of this vector, which is -4, -7. So when we combine those together, what should we get?
-5, -4.
-5, -4. Everybody good with that? Easy enough? How do we find the magnitude of 1/2 of u?
First find 1/2 u and then find the
All right,
magnitude.
so what's 1/2 of u? That's just multiplying u by the scalar. So that should be 1/2, sorry, negative 1/2 and 3/2. And then finding the magnitude of it is just using the Pythagorean theorem. So this ought to become the square root of negative 1/2 squared plus 3/2 squared. And what does that give us? That's 10/4 inside of there. Or root 10 over 2. So that vector has a magnitude of root 10 over 2. Any questions or issues with that? All right, some more very basic operations and rules that you should just generally know for vectors, especially if you're planning on going forward in math and science in college. Most of these are the same sort of rules that we have with basic algebra, right? Or just basic arithmetic. Right? The addition of vectors is commutative, so u plus v is the same as v plus u. Or if you have 3 different ones, you can associate them using the associative property in any way you want. So u plus v first plus w is the same as u plus v plus w. If you add a 0 vector to a vector, you just end up with the vector you started with. If you add a vector and the opposite of that vector, you get 0. If you multiply a vector by the scalar 0, you get 0. If you multiply a vector by the scalar 1, you just get the vector that you started with. And just like the addition was commutative and associative, so is the multiplication of vectors with constants. And the distributive property still applies. So if I have 2 vectors being added together times a scalar, I can apply the scalar to both of them. Or if I have 2 different scalars multiplying by a vector, I can distribute that vector to both of the scalars. All those rules on the bottom, okay? They're pretty straightforward rules, I think.
Yeah.
Okay. And then up on the top, there's 2 other things we're talking about here. That one is the vector v over the absolute value of v. So if you take the vector and divide by its magnitude, then that new vector should have a magnitude of 1. And we call it the unit vector or the direction vector, because when you take it into its component form, it's just cosine theta, comma, sine theta. And so this this idea of the direction vector allows us to take the inverse tangent of the y component over the x component to find the actual direction of the vector. Pretty straightforward, I think. All right, let's see if we can do a vector problem. So I'll give you a second to read it and then we'll try to work through it here. So let's first draw a quick picture of what's going on here. We've got an airplane that is flying due east, right? So it's going this direction, and it's doing that at 400 miles an hour. Okay. I guess we could label that, sure, 400 miles an hour. And it's also got a tailwind that's acting on it, and that tailwind is 60 miles an hour, and it's at an angle of 30 degrees north of east. So this would be a 30-degree angle here. And this is blowing at 60 miles an hour. And so our question is asking us, if the plane doesn't make any corrections to its direction, we want to know what is its new ground speed and direction. So it's trying to fly 400 miles an hour due east, but it's being blown a little bit off course. So let's first figure out what vector represents our velocity. So let's think about a velocity vector of the plane by itself. What should the velocity vector of the plane by itself be without the wind acting on it at all?
Just 400 and then comma 0.
That's right. It's got an x component of 400 and it's got a y component of 0. That should be an easy one. All right. What about the velocity vector of the wind?
Be like 60 cosine 30 degrees, comma 60 sine 30 degrees.
It ought to be 60 cosine 30 and 60 sine 30. Exactly. Everybody good with that, right? The cosine is always with the x component and the sine is always with the y component, right? If we were to draw a right triangle out there, we could see the x and the y components in that. Everybody good or no?
Good.
All right. So what should the new vector of the plane be? We should simplify this first, I guess. What does this simplify to?
30 root 3 and 30.
30 root 3 and 30. Okay. And so now that we have a nice simplified vector for the wind and a nice simplified vector for the velocity vector, we'll call it the new velocity vector with the wind, ought to just be the
Resultant.
vector. It should be these two added together, which ought to just be 400 plus 30 root 3, comma 30. Easy enough? Yeah?
Mm-hmm.
All right, so now we have a little bit of a problem though. This is not what the question was asking us. What's the question actually asking us?
The speed and direction.
Speed and direction. So we have a velocity vector. To find the direction of motion, we should just be able to take the inverse tangent of the y component over the x component. And to find the speed, how are we going to find that?
Magnitude.
It's the magnitude of the velocity vector, exactly, the absolute value of the velocity. So I think we'll probably need a new page to do those. Our speed ought to be the absolute value of what was our vector? It was 400 plus 30 root 3, comma 30, right? Which ought to be the square root of 400 plus 30 root 3 squared plus 30 squared. And what does that come out to be? About. Rounded to 3 decimals.
452.956, I think.
452 point what?
956.
956 miles per hour. Don't forget your units. Huh? Everybody okay with that or no? And our direction ought to be the inverse tangent of 30 over 400 plus 30 root 3. And what does that come out to be?
3.8.
What is it?
3.8.
Let's give it 3 decimals. Yeah, to 3 decimals.
Yeah, 3.97. So
That's only 2 decimals.
sorry, 3.798. 3.798.
All right, and is that in degrees or was that in radians? I assume that was in degrees. That better be in
That's
degrees.
degrees.
And if that's that should be, let's see, we're going to go north of east because it's blowing us up, right? Everybody good with that or no?
Good.
All right. Any issues with that nice vector problem there?
Are the units needed for the degree since it's implied that's in that direction?
No, you're probably good if you didn't write that north of east there. It's probably all right. All right. So if we have a particle that's moving along a smooth curve in a plane, and we're given its position at any time t, we should be able to write position vectors, velocity vectors, acceleration vectors, and figure out the magnitude and the direction of motion for any vector like that. So the nice thing about this is nothing really changes from any of the derivative stuff we've done with motion before. The derivative of the position vector is just the velocity vector, and the derivative of the velocity vector is just the acceleration vector. And you know, the way you find those is you take the derivative of the x component and the derivative of the y component, and that's your new velocity vector. And you take the derivatives of those, and that becomes your acceleration vector. It's just pretty straightforward. So I'll give you guys a second to look over that and make sure you don't have any questions on any of those. And then we'll move on and do this with some function. Everybody good there or no?
I need some more time.
I don't know if we have enough time. I guess we can wait. Yeah.
Okay, I'm good. Sorry for.
So it goes. All right. So we've got a particle that we've got moving in a plane. Its position is given by sine t squared over 2. If that's the case, what should the position vector be?
Sine t, comma t squared over 2.
Yep. We're given the position point at any point. The vector is just, the position vector is just that same 2 components as a vector. So what should our velocity vector be?
Cosine t comma t.
Exactly, just cosine t comma t. Derivative of sine is cosine, right? And the derivative of t squared over 2 is just t. And what should our acceleration vector then be?
Negative sine t comma 1.
Negative sine t comma 1. Perfect. And if we were going to try to describe the motion of the particle at a specific point, let's say the point t equals 6, the position of it should be very easy. What's the position of it? Should just be the position point or the position vector evaluated at 6, which will be the sine of 6, comma 18. but how do we describe the motion? What is the angle that this thing is traveling at? It should be the inverse tangent of which vector? And the y.
Velocity?
Yeah, the velocity vector. It's always going to be the velocity vector. So it'll be the y component over the x component of the velocity vector. So at t equals 6, the y component is 6. And the x component is just the cosine of 6. And what does that come out to? Radians or degrees? I don't care which one.
.412 radians.
All right. Anybody know what that is in degrees offhand?
80.589.
Cool. So its direction, it's moving in that direction at that exact point, 80.589 degrees or 1.412 radians, and it's the point sine 6, 18. So real quickly, let's just for fun take a look here in Desmos. That's not what we're looking at. What do we have here? We had sine of t, right? And then t squared over 2. And we're going to look at this from 0 to 6. This is what this particle should look like, or its motion should look like. It's moving along this curve all the way up here to the point that is sine of 6, 18. And it sure looks like the direction that it's traveling in at that point is about 80 degrees, right? It's about 80 degrees north of east, right? Or 80 degrees coming around counterclockwise from the positive x-axis. Everybody good with that?
Should be.
You should be, yes. So a lot of these vectors will come up with kind of cool little paths that the particles would take in the plane. All right, let's do another one. So we've got a baseball player hitting a ball, and blah, 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 blah. I'll let you read it. And then you guys want to see if you can go through and start this one off with the position vector and the velocity vector on your own?
Sure.
All right, let's make sure you can get the position and the velocity vectors, and then from there, we will work together to get the rest of it. So I'll give you guys like 2 or 3 minutes to do that. So what did you get for your position vector?
I got 110t cosine 60, 110t sine 60.
All right, so we have 110t times the cosine of 60. So that's the x component, right? So the ball's traveling at 110 feet per second, and it's at an angle of 60 degrees. So 110 times t for the, this is velocity is 110. So the position would be 110 times number of seconds, 110t cosine 60. That's good. And then you said 110t sine 60 for the other?
Yes.
Anybody have an issue with that?
Isn't it gonna like change as the ball like continues?
Yeah, so there's a second force besides just the fact that it was hit at this 60-degree angle above the horizontal. There's a second force acting on it, right? What is the second force that's acting on it?
Gravity.
Gravitate.
Gravity, right? And if we're doing stuff in feet per second, what is the acceleration due to gravity in feet per second? Anybody? Should be negative 32 feet per second squared. Haven't you all taken a physics class sometime?
It's always in meters per second for us. So
Meters per second squared, yeah.
yeah.
Yeah, it's better.
Why are you
way-
using such antiquated units?
Because that's what the test does. Otherwise, I wouldn't.
That's
I
mean.
understand that the metric system is far superior, but I can't help it. The College Board is full of, I shouldn't say anything. All right, so if the acceleration due to gravity is negative 32, what's the velocity due to gravity? Change in velocity should be just negative 32t. And what would the position then be? Right, these are just simple integrals, right? Negative 16 t squared. So the position is affected by a negative 16 t squared. So we need to subtract that from here, minus 16 t squared. Good or no? So anytime you have a particle or an object that's being affected by gravity in the y direction, that's negative 16 t squared in feet per second. All right, so what does this come out to be if we simplify this down a bit? The 110 t cosine 60 ought to become 55t. And then 110 t sine 60 ought to become what? (55√3) times t minus 16 t squared. Good or no? Yes, no, maybe.
Yeah, good.
With the negative 16 t squared came from an integral, right?
Yeah, it did, yeah. But that's just something now we're just going to know that the acceleration due to gravity is negative 32. And so the position, the effect on the position vector is always going to be a minus 16 t squared if they do it in feet per second.
Okay, I see.
Yeah.
So you're just able to subtract an acceleration vector from a position vector?
I didn't subtract an acceleration vector.
You
I
said the
turned that
60.
I turned that acceleration into position, right? By integrating acceleration to velocity to position.
Oh, okay.
Everybody good with that now or no? Okay. So what does our velocity vector become then? X component ought to be
55.
55, and our y component ought to be 55√3 minus 32t. Good or no?
Good.
Okay. At what time does the fielder catch the ball and how far is he from home plate? So how are we going to figure out when he catches the ball?
You
He's
can
reached that
solve
8.
for-
Say that
Oh,
again.
sorry. You
Go
can
ahead.
solve for when the second part is equal to 8.
Right. We want to know when does the y component of the velocity vector equal 8. So when does 55√3 minus 32t equal 8? And you should be able to tell me what that is. That should be at t equals what? Not the velocity, sorry, not the velocity, the position. 55√3t minus 16t squared equals 8. So when does that happen? When does that equal 8? value for t there?
.869 seconds.
Good to me. Everybody else agree with that?
Yeah, I got the same thing.
All right. And so if we want to know how far is he from home plate, that would be the x component of our position vector, 55t, at 5.869. So that'll be 55 times 5.869. What does that come out to be? Probably 300 something.
322.795.
322.795, and that should be feet. Right? Everybody good with that? All right. How fast is the ball traveling? That should be a speed, right? So we need to find the absolute value of the velocity vector at t equals 5.869. So that ought to be, well, we could do the absolute value of 55 comma 55 root 3 minus 32 times 5.869, which ought to be the square root of 55 squared plus 55 root 3 minus, I don't know, whatever that is, 32 times 5.869 squared. And what would that come out to be? Does that make sense to everybody, how we're finding this speed?
Yep.
Okay, perfect. So what do we get? How many feet per second?
$107.648.
Everybody agree with that or no? Good or no? All right, this one should be really easy. What is our velocity vector? What's the velocity vector?
3 cosine 3t, comma negative 5 sine 5t.
All right, 3 cosine 3t, negative 5 sine 5t. What's the acceleration vector? Ought to be the derivative of that, negative 9 sine 3t and negative 25 cosine 5t. If I asked you what was the direction of motion at a certain t value, what would you do?
take the absolute value of the vector function, or of the velocity vector.
If I was looking for the direction of it. If I was looking for direction, I would take the inverse tangent of the y over the x components of the velocity vector. If we're looking for speed, then we'll take the magnitude of the velocity vector. Let's real quick look and see what happens to this one when we graph it. Some of these come out cool. This is sine 3t, what was it, cosine 5t? Yeah, that one comes out looking cool. This is the path that this particle takes through this plane. Just repeats this same pattern over and over and over again.
We can't see.
Oh. Now you can. Isn't that cool?
Where does it start?
Right there. So just sort of starts looping around like that. And sort of does a thing like that to get all the way through it. Isn't that exciting? All right. Ignore these last two things down here. I wanted to actually get rid of those, but I couldn't get the toolbar to show up on this today for some reason. So what's your velocity and your acceleration vectors here? What's your velocity vector?
4 cosine t and 2 sine t.
Easy. -2 sine t. And acceleration vector ought to be
-4 sine t, comma -2 cosine t.
good. If I want to find the velocity at pi over 4, that's just the velocity vector evaluated at pi over 4. So that would be 4 cosine pi over 4, -2 sine pi over 4, which would simplify to what? Cosine of pi over 4 is √2 over 2, right? So that's just 2 √2. And then -√2 if you simplify the second part down. What's the acceleration vector? It ought to just be at pi over 4. What should that be if we plug in pi over 4? That should become -2 √2. And then -2 cosine t ought to give us -√2 again. Good or no?
Yeah, that's good.
And how do we find the speed?
The absolute value of the vector function.
All right, absolute value of our velocity vector at that time. So absolute value, we'll call this speed equals absolute value of 2 √2 -√2. which is the square root of 2 root 2 squared plus negative root 2 squared, which gives us what? Square root of 8 plus 2, or root 10. So our speed is root 10. And what about our direction? Ought to be the inverse tangent of what?
Negative root 2 over root 2, or 2 root 2.
Negative root 2 over 2 root 2, which is the inverse tangent of negative 1/2, which is what? You need a calculator for that one, probably.
Negative 0.464 radians.
Negative 4 point what?
0.464 radians.
0.46. Is that an acceptable answer?
No.
No.
No, because it needs to be a positive one. So we should get 2 pi minus 0.464. Ought to be the same. So that should be the direction. 2 pi minus 0.464 radians, whatever that comes out to be. Good or no? That's it for vectors. The vectors for this class don't get any more difficult than that, for the most part. We'll do some stuff with integration with them when we talk about integration, but other than that, that's as difficult as the vectors get. Any questions or issues with that?
Should be good.
All right. Cool.